Good afternoon, everyone. Welcome to the Astronomy Department cycle of seminars. Many thanks for joining us here or through our YouTube channel. And today's speaker is Professor Omer Bromberg. Many thanks, Omer, for accepting our invitation to be here today with us.
My pleasure.
So I am going to briefly introduce Omer. He obtained his PhD degree from Tel Aviv University and was a postdoc researcher at the Hebrew University and also at Princeton. And currently, he's a professor at Tel Aviv University. And Omer works on various topics related to relativistic astrophysical systems and on magnetohydrodynamic simulations of astrophysical jets. His research includes running large-scale 3D magnetohydrodynamic simulations of jet formation and propagation and study their physical properties. And today, he's going to talk about energy dissipation channels in highly magnetized relativistic jets. So let me ask everyone to please turn off the microphones and cameras during the talk. And if you have a question, you can raise your digital hand here in the Google Meet, or you can write it down in the YouTube chat, and the questions will be asked after the presentation. So, Omer, whenever you are ready, you can start.
Okay, I will start, but I warn in advance that when I do the presentation, I don't see anything. So
don't worry, we will talk to you if something is happening. Yeah.
Okay, so one moment. Okay, do you see my screen?
Yes.
Excellent. Okay, so hello everyone, and thank you for inviting me to give a seminar at your institute. It's actually the first time I'm visiting this your institute, but I know quite a few people here, so it's actually kind of like giving a talk to a home audience. So I'm going to tell you today about my current understanding on the physics of relativistic jets, which is based on several of my recent research that I'm going to present to you. You see here a list of my collaborators which contributed to the research. Also, one of my collaborators was a postdoc at your institute, Chandra Singh, and you will see some of his work during the presentation. So since this is basically a lot of you are studying radio astronomy, I thought it would be best to start with a little bit of to start talking about radio galaxies. I think it's most appropriate. So radio galaxies are basically part of a large group of AGN family, but they also belong to a larger group of astrophysical objects which host relativistic jets. Among these objects are gamma ray bursts, microquasars, and we think that some supernovae are also host or hide relativistic jets in them. Though the jets in these objects are varying both in size, activity, and emission properties, they are thought to be powered by a common mechanism. And this mechanism is an electromagnetic extraction of rotational energy from a compact object, most likely an accreting black hole. And the different emission properties that we see are coming either from the different black hole masses, accretion rates, environments, observational angles, and also likely different types of dissipation mechanisms. And this is part of the things that I'm going to discuss in this talk. If we want to discuss, I want to discuss a little bit about how the launching process works in Poynting flux dominated jet. These jets are launched by electromagnetic process, so they are dominated by electromagnetic Poynting flux at their base. So basically, you can envision this launching process by this very simple toy model. You take a perfectly conducting sphere, and this sphere is threaded by magnetic field. Here you can see this this B, and it rotates. Now, since it's a perfect conductor, on the surface, the electric and magnetic forces should balance each other. So the Lorentz force should be 0. So it dictates that an electric field is formed in the theta direction, which balance the magnetic force. Now, another thing that has happened since the sphere is a perfect conductor, as it rotates, due to flux freezing on the surface, it drags the magnetic fields with it. So if we rotate the sphere a little bit, you see that the magnetic field is basically dragged to the left, and this creates a toroidal component on top of the radial component that we saw here. Now, this toroidal component is perpendicular to the electric field, which is in the theta direction, and the cross product of these two components produce a Poynting flux that is moving in the radial direction out of the black hole. And this Poynting flux is carrying basically the rotational energy of the rotating sphere. It is a very efficient way to extract energy. For example, in supermassive black holes, I don't know, it's with magnetic fields of about 10 to the 5 Gauss, you can get up to 10 to the 48 ergs per second with this mechanism. However, the energy that is extracted in this way is carried by very long wavelengths and that flow out along the jet. And it is not expected to be observed. And yet, when we look at the jet, we see many, many different emission sites on many different scales, starting from a few gravitational radii, as the new Event Horizon telescope showed us, and it goes up to 10 to the 7 gravitational radii and even more. And this energy is radiated in all wavelengths, from radio until X-ray and sometimes even gamma rays. So it means that that there is some kind of a dissipation mechanism that is working along the jet. And since the emission properties are rather different between the different places along the jet, it is most likely that there is more than one dissipation mechanism that is at play. And the question is, how does dissipation mechanism work? Where in the jets they are working, and how does the electromagnetic energy is transformed into the radiation that we observed? Another question is, what is the acceleration and the emission mechanism that are responsible for this energy release? So what I'm going to do in this talk, I will present several activation and dissipation channels in Poynting flux-dominated jets, and discuss the pros and cons in each mechanism and some observational prediction and some problems that we still have. So let's start with the first dissipation mechanism. And this dissipation mechanism is coming from a type of instability that is known as Kink instability. So what is Kink instability? Basically, if you take a magnetic field, which is dominated by toroidal field, this field tend to be unstable and develop kink modes. Basically, kink modes create a helical twist in the jets and lead to reconnection. Do you see my hands right now?
Yes.
Yes, excellent. Do you see the spring that I'm holding?
Yes.
Okay, so you can imagine this spring as this jet, because basically where you start, where the magnetic field that is propagating outward is propagating as a helical mode. Basically, you have both toroidal and poloidal magnetic field moving out. So a kink instability is this type of deformation that is occurring at the jet. Okay, and this basically leads to reconnection of the magnetic fields, and that leads to energy dissipation. Now, the basic time unit for the linear growth of kink instability is a fraction of the time it takes a fluid element to circle around the jet, around the periphery of the jet. But this time unit is measured in the rest frame of the plasma that is moving along the jet. So if you want to translate that to the observer frame or to the star frame, if you want, you need to multiply it by the Lorentz factor. And so you can imagine that if this time unit is a function of the time it takes a fluid element to circle around the jet, So kink instability will tend to evolve faster in narrow jets that are dominated by the toroidal field. And the time that it takes this kink instability to grow to the nonlinear stage, where the deformation is actually felt and starts to affect the jet, is something like 10 times. The e-folding time is about 10. Okay, so 10 times of this T kink. So what we want to do is we want our jets to be narrow and dominated by toroidal field. The problem is that it is not easy to make narrow jets. So let's move back a little bit to the jet close to the launching site, and see what is happening to the magnetic field as it starts to accelerate. So initially, what's happening is that the acceleration is done on these radial fields that are anchored to the central object. Now, in order, basically, what the acceleration is doing is that we are transferring energy from the toroidal component into the poloidal component. In other words, we start by a spring which is very, very, very winded, is tight and winded very tightly, and then the spring gradually becoming unwinded. So it is expanding, and this is the acceleration process in magnetic jets. Now, if you think of it, when you have a toroidal and poloidal field that are propagating outward, the poloidal field tends to drop like r squared to preserve poloidal flux. The toroidal field will drop like 1 over r. So as the jet is expanding outwards, it wants to become more and more dominated by the toroidal field, which drops slower. However, because the jet is continuing, the spring is continuing to try to be unwinded, so these two components, the toroidal and poloidal components, are maintaining a balance. So as the jet accelerates, BP and B phi are roughly at the same order of magnitude. So, and the effect of this is this. So toroidal field is acting like a rubber band. It has something that is called hoop stress, that is try to take the toroidal field and compress it together. And this hoop stress, you can see it in the blue arrow, is pointing inwards toward the jet. However, since it is balanced, since the toroidal field is balanced by the poloidal field, the poloidal field poloidal and toroidal field has also tendency to create a magnetic pressure that is pushing outward. So during the time the jet accelerated, the hoop stress that is pointing inward is balanced by the pressure gradient that is pointing outward, and we don't have any collimation. The jet cannot self-contract. It cannot collimate itself. So it will continue to expand on radial trajectories. At some point, the acceleration will stop. The acceleration will stop at the Lorentz factor hits some limit, where the fast magnetosonic velocity is where the flow of the material is too fast, and then different parts of the jet can no longer communicate with themselves. This is very similar to what happened with hydrodynamic jets. For some of you who work on hydrodynamic jets, the jet is becoming uncausally connected. At this point, you can no longer continue this efficient passage of energy from the toroidal component to the poloidal component, and the jet basically starts to accelerating. And it's accelerating very, very, very slowly. However, since it can no longer change energy between the toroidal and poloidal component. The poloidal component now drops faster, like r over 2. Toroidal component continue to drop like 1 over r, and the jet is becoming more and more dominated by the toroidal field. Okay. However, since I have no longer a causal contact along this loop, each part of the jet does not know that it is part of a loop of toroidal field. So the hoop stress is not efficient. So the jet stops accelerating, it's continued to move outward, highly magnetized, but it cannot self-contract anymore because different part of the jet is out of causal contact. So both during the inside the region where efficient acceleration work and outside of the region where the jet can no longer accelerate, in both of these times, the jet cannot collimate itself. And I need an outside pressure to compress the jet and collimate it. So this is the importance of the medium in relativistic jets. So when we think of medium, we can think of two types of collimation. One type of medium that collimates is wind. Suppose that the jet is ejected into a region where we have this wind that is blowing outward. This wind will collide with the jet and it will collimate it. Now, this type of collimation generally tends to create conical or parabolic jets. These jets are not very narrow, not too narrow. The Lorentz factor in these jets tends to be fast. And as you remember, the time for Kink evolution is measured in the rest frame. So if you have highly relativistic jet, this time is increased by a factor of gamma, and this jet will tend to be stable to Kink. Another type of medium, these are stationary mediums, like in the case when a jet is expanding into the interstellar medium, in the case of AGNs, or if the jet is expanding into the envelope of the star that is surrounding it, in the case of long gamma ray burst. In this case, the propagation of the jet through the medium will create sort of a cocoon of shocked material around the jet, as you can see here. The pressure in this cocoon tends to be uniform, and a uniform pressure will create a cylindrical jet. Now, these jets will be very narrow, and the flow in this jet will tend to be rather slow. These jets can kink. So I'm going to discuss about this. These are going to be the focus of my talk when I will discuss the kink instability. When we think of AGN jets, actually these two types of mediums may exist. Close to the inside if you want the Bondi radius or close to the black hole, there is a strong wind that is coming from the accretion disk, and the region around the jet is dominated by the wind, and therefore the jet collimation there will create jets that are rather parabolic. These types of jet you can actually see in these types of geometries. Actually, you can see, for example, in the galaxy M87. At large enough distances where the wind stops being effective, you are dominated by the ISM, which is a stationary medium. So when the jet is propagating there, it will develop this cocoon that will tend to create these cylindrical jets. And in the region where the jet material is moving out of the wind region and into the stationary medium, there is a change in the jet geometry. What's happened is that the jet stop transforming from being colloidal, or sorry, from being in a parabolical shape. It starts to be cylindrical. When it is doing that, the hoop stress become effective again. And when it's become effective, immediately it affects the jet and it contracts it. And this transition into the stationary wind, into the stationary region, are usually signified by the formation of very narrow nozzles, as you can see here in this image. And these nozzles are the flow there. The jet there is very narrow. Flow there tends to be very slow, and field lines may become affected by the kink instability. And actually, many people already speculated that within these nozzles, there is effective dissipation that is happening due to kink instability, and people investigated that during many years. An example for this type of transition you can see in the galaxy M87, and in a special feature in this galaxy, which is known as HST1. This is a luminous knot that radiates between radio to X-ray. it shows massive energy dissipation. It is a very effective emitter, and it is located about something like 100 parsecs from the central black hole. And the region where this M87, where this HST1 is located, coincides with a shift in the jet geometry. At smaller radii, the jet geometry is rather parabolic. You can see it goes like z to the power of 2. And above this line, actually, the jet seems to become radial. However, these measurements are, we do not know how long they are lasting. So it could be that what we see is the moving out from a nozzle. There are some indication that the jet radius is becoming smaller at this region. However, this is not certain. However, this can be signify the transition from a weak to a stationary medium. So what I did with my associate Sasha Tchaikovskoy, we try to investigate what happens within these nozzles in global MHD simulation. And basically what we found is that as the plasma go through this type of nozzle, indeed it becoming kink unstable and dissipate about half of its energy into heat. However, the problem was that in our global simulations, we did not have enough resolution to actually follow this instability to small details, and we could not say whether this 50% of dissipation is actually a robust thing, or was it just a function of the boundary and initial conditions that we use. So in a follow-up research, what we did is that we ran local simulations where of plasma columns, where the magnetic field there has a toroid, has a helical shape. And we investigated the evolution of the kink instability. And basically what we saw is that the kink instability have several stages that it is going through, and I'm going to show you these stages with this movie. But this movie is showing a 3D image of the z direction of the electric current of Jz. Okay, I'm just showing here two colors in order to so you can be able to distinguish between the different layers. Okay, and so as the kink evolves, initially the core starts to twist. This is like an initial phase of some readjustment, and this is the kink this is the kink modes that starts to grow. Now, as it continues to grow, these kink modes begin to merge with each other, creating a current sheet between them, and it drives a reconnection in the helical current sheet that is produced. At some point, this helical current sheet begins to break due to all kinds of instabilities that are happening within it, and the kink continue to evolve until it relaxes. And when it relaxes, the jet is dominated by small-scale turbulence, which continue to dissipate the energy through stochastic dissipation over a slower rate. Okay, the relaxation is obtained when the magnetic field configuration reaches a sort of configuration where the current along the z direction is proportional to the where the total current, is proportional to the magnetic field. This type of configuration is known as Tyler state. It was investigated before mostly in the context of tokamaks. And we show that also in the case of high sigma jets, of relativistic jets, when you reach this Tyler state, then the kink instability relaxes. So basically what happens if you look at the dissipation as a function of time, you see that there is a stage where Kink instability is effective, and this is the stage where you have a relatively rather fast dissipation. And then when Kink instability relaxed after a few hundred up to or 1,000 jet crossing time, then you start to have this turbulent dissipation that is continue at a rather slow rate. We show that indeed about 50% of the toroidal magnetic field can be dissipated in this process. We also show that the dissipation rate is something like 0.1 of the crossing time of 0.1 of the rate that it takes to if you want to cross the jet or about that. And this is consistent with the sideways motion of the Kink mode. The turbulent motion that continues to dissipate the magnetic field will basically dominate the evolution of the plasma above the nozzle. So if you think, so this simulation were conducted on a stationary column, but if you think of the situation like as we are moving with the flow as it passed through the nozzle, so inside the nozzle, the flow will dissipate it by this Kink instability, and as it goes out, the dissipation will relax, and turbulent dissipation will continue to dissipate the magnetic field above this nozzle, however, at a smaller rate. There were two problems with this study. One problem was that we could not follow the turbulent dissipation to long enough time, so we did not see how effective, how far it can continue to dissipate. This is, by the way, an important question. I will reach to it later. And the second important thing is that, remember when I told you how the jets are launched? The jets are launched by the rotation of this perfect conductor, or the black hole, or the neutron star, or whatever that is rotating at the base of the jet. Now, when you rotate your magnetic field, basically this magnetic field, as they propagate outward, they carry omega with them. So they carry angular momentum. The plasma within the jet is actually supposed to rotate. And with this study that we did, we neglected rotation. So the topic of a follow-up study that we are now conducting, I'm conducting with Anya Chashkina and Bart Riperda and Sasha Filipov, both of them from the Flatiron Institute. And Anya Chashkina is working with me in Tel Aviv. Sorry, we're conducting a follow-up research where we apply rotation now to the plasma. Now, what rotation is expected to do, it was speculating in the past that the rotation will add actually stability to the jet. So the question is whether a rotating jet can kink. Is all this study relevant to astrophysical jet? Maybe since the plasma is rotating, kink instability is not effective. And why are you telling us all of this? Because it is just non-relevant to relativistic jets. So what I'm going to show you here is I'm going to show you a movie of the evolution of this Kink instability in rotating jets. Now, these simulations are much more evolved than the simulation that we conducted in the past. They are done with a resistive code that has an AMR capability, which means that we can resolve much better the small scale turbulence. And you can see that as the simulation starts, on the left side, you see the density, on the right side, you see JZ. The evolution indeed is slower. The Kink instability takes longer to grow than in the non-rotating jet. However, when it starts growing already, when it goes into the non-linear stage, what we see is that it's dissipation evolution, both the dissipation rate, the transition to the turbulence phase are very similar as to the non-rotating case. And another, here you can see how the current sheet break, and now you can see the small scale turbulence that are evolving in the jet as the jet continue to rotate. And another important thing that we see that is happening, that as this dissipation evolves, angular momentum is basically taking out from the central region and move to the outskirt of the jet. So basically the jet slows down. So this simulation did not last long enough, but the hope is that maybe if the angular momentum will drop to low enough value, we will be able to reconstruct the stable conditions that we saw in non-rotating jets. So here is the evolution on the timeline. On the left side, you see the total angular momentum as a function of the radius from the center of the jet, and on the right side, you see the dissipation rate, where non-rotating jets are shown in blue and red, and the rotating jet in this case is shown in purple. And you can see that indeed the dissipation starts later, but when it starts to dissipate, when the Kink instability kicks in, the dissipation rate is very similar to what we see in other cases. And another thing that you can see is that the angular momentum peak is basically start to decreasing and move outwards. So at later stage, you can see that the angular momentum is already much lower than what it was initially. So we need to continue follow this simulation and see what will happen. So this is a work in progress. So there is a hope that we will gain understanding on the evolution of Kink instability in MHD jets. However, if we want to discuss about what will be the emission signature from these types of jet, MHD simulations are not enough. The reason why they are not enough is that they are simulating only the average fluid properties, and we do not know what is the actual energy of the individual particles that can accelerate in these in the currents that are formed. So for that, if you want to track individual particles, you need to use peak simulations. Peak simulation, basically what they do is they follow the evolution of individual particles, or if you want macro particles, within electromagnetic field. Basically, they evolve the evolution of the particles in the electromagnetic field, and then they take the effect of this particle embedded into the electromagnetic field, evolve the electromagnetic field, and vice versa. This is how they progress with time. And they can actually give you an information about how individual particles are accelerated within the currents that are formed in the reconnection region. The problem with these types of simulation that they are limited to simulating very small regions because they need to resolve the Larmor radius of individual particles. So this is definitely, these regions are much smaller than the entire system. However, what we wanted to see is what will happen, what will be the global evolution of the system, how the global system will behave if we take large enough scale separation, meaning that the resolution, if you want, of the simulation, of the peak simulation, will be very large. What we discovered is that, so we ran this global peak simulation of non-rotating jets, and we compare them to the simulation of the hydrodynamic jets that we run, that you see here in the top. And we discovered that if you take large-scale peak simulation with large enough scale separation between the size of the system and the skin depth, and if you want the length scale of motions of Larmor radius of individual particles, if you are able to resolve large enough scale separation between these two parts, you get a consistent evolution between the MHD and the peak simulation. So we could actually reconstruct the Kink evolution within the peak simulations. What we saw, and we're able to track the acceleration of individual particles. We could show that the acceleration is actually happening in two stages. First, there is acceleration inside the helical current sheet that is produced as the Kink modes are evolving, and this acceleration give you here. I'll show you here. Give you here a non-thermal tail of the accelerated particle, although the slope of this tail is rather steep. Okay. Secondly, when the current sheet breaks down into small-scale turbulence, the effect of this turbulence is mostly heating. So we get a lot of heat that is producing, but the non-thermal tail is disrupted. Again, these simulations are limited, and we could not, and I could definitely not say that this is the definite result. The reason why the result is limited is that we cannot resolve, for example, the full plasmoid change within the reconnection layer, and we could not. So we could definitely could not resolve the actual physical processes that are happening within the reconnection layer, and we could not resolve the small scale turbulence. So whether there is a second stage of second order Fermi that is happening within this the plasma as it moves out of the into the turbulence regime, we could not see that. And we hope that with future simulations, that will have a better resolution, and we will be able to resolve this type of acceleration and have a better answers. Okay, so we understand that what may happen within this collimation nozzle, but is there a way to test that observationally? So as it happened, at least I suspect that there is. When you look at blazars flares, you can see that there are some types of flares that show very specific behavior. If you look at the flare of this type of flare, what you see is that this is the flux in optical in R band. Okay, and during the flare, you can see that there is a rise in the polarization signature of the flow, together with the rotation of the polarization vector. Okay, now this indicates that something that, first of all, magnetic fields are involved in the creation of the flare, and something very strange is happening to this magnetic field. There is rotation by about 400 degrees during the flare. Okay, one possibility that can create this type of rotation is the passage of a plasma blob through a collimation nozzle. Now, as the plasma blob is passing through the collimation nozzle, it starts to emit because the dissipation takes effect, and it's also rotate. The plasma blob they rotate by itself as it moves through the nozzle, and this may create this rotation of the polarization vector. We are now trying to develop a tool that will analyze the time-dependent polarization from relativistic magnetized plasma. And if we'll be able to do that, we'll be able to see if we can reconstruct this type of this very specific type of flares that we see, and maybe we can have like an observational signature for the passage of plasma that is dissipating energy inside the blob, inside the collimation nozzle. Sorry. So this is what I wanted to tell you about the kink instability. How much time do I have until the end? What is the length of the talk? Is it 45, 50?
You can do 45, no problem. Yeah.
Okay. So in 10 minutes, I think I'm okay. So kink instability is a very efficient way to dissipate about half of the jet magnetic energy within intermediate distances, the distances of about 10 to the 3 to 10 to the 5 gravitational radii. However, it have several drawbacks. One disadvantage is that when the plasma is leaving the collimation nozzle, basically what Kink is doing, Kink is taking energy from the toroidal field that is giving it into thermal pressure. Now, the relaxation is happening when there is a rather equilibrium, if you want, equipartition between the magnetic pressure and the thermal pressure. So when the jet plasma is leaving this nozzle, it is a kind of the weird state of a hydromagnetic jet with sigma or plasma beta of order of unity. Okay. Now this type of plasma is not very convenient to us because it cannot effectively create shocks. Shocks are not effective there, so it cannot dissipate further energy via shocks. And it cannot produce fast reconnection anymore because fast reconnection requires cold plasma. So the dissipation with turbulence may help as it continues to evolve there, but however, this situation is still the jury is still out on this. So I cannot say whether the turbulent dissipation can help. But however, the condition of this plasma makes it hard to effectively further to dissipate energy at larger distances. For example, if I want to create a gamma ray burst, I need to dissipate this energy at very large distances, and I cannot do it through shocks. I cannot do it for reconnection, so I'm in problem. So I have a problem. Another problem that I have is that all these emissions, all the very, very efficient emission that we see at close proximity to the black hole cannot come from Kink instability, because the jets there, if they are continuous jet, they are stable. So it cannot account for emission that comes from close proximity to the black hole. So this is a very limited way to give me energy at a very narrow regime. So we set up and try to think of another mechanism that can dissipate energy both at large distances and at small distances. And this type of mechanism I want to present to you now. So if you look at your jet, so here in this picture I'm showing you an illustration of the jet with the helical field, and suppose that there are regions in the jet where the direction of the field is reversed. You see this region is colored in red. So you see these arrows here. The arrow is pointing to the right. Here the arrow is pointing to the left. And suppose that this jet is now contracting. I don't know. It's colliding with something, or maybe this region is moving faster than this region. So you produce collision here. So here I can get an almost complete dissipation of the magnetic energy via reconnection, via like almost a planar reconnection, like the classic reconnection reconnection test that people did in peak simulation. This type of jet is known as striped jets. Okay, and it's because the name is coming from stripe pulsar wind that is coming on the equatorial plane in pulsar. I don't want to go into it, but this is the name that is given to it. It's like stripe of the magnetic field is going to one direction here and to the other direction here, and it's like that. It's like a layer. So this is a very efficient way that can give you a dissipation at different distances. However, now there is a question of how we can produce these types of jets. Now, to remind you, the jet is launched by winding of poloidal field. Okay, and the poloidal field, basically the poloidal field in the case of a black hole is supplied from a disk. I will show you a simulation soon that Anya did, and basically what happens is that if you have a magnetic field in the accretion disk, and this matter is accreted onto the black hole, the magnetic field is accreted with the matter and creating this closed loop. And as the black hole is rotating, you wind this poloidal field and you create a jet. If you want to create a stripe jet, which is an intermittent jet that is sometimes launching a magnetic field in the right with the right helicity and sometimes with left helicity, what you need to do is you need to switch the polarity of the magnetic field that is threading the black hole, like I show here in this animation. Okay, so a mechanism to switch the polarity of the magnetic field on the black hole horizon was first thought by Carl Parfley in 2015 and was investigated by him and by others. But these types, with certain types of simulation, which is known as force-free simulations. These simulations simulate only the evolution of the electromagnetic field. They assume that the plasma the plasma is no effect of the electromagnetic field. And in order to produce these loops, basically what they did is that they take on the equatorial plane, you see they built loops with opposite polarity. Here you can see with clockwise and here with anti-clockwise polarity. And they advected these loops by hand into the black hole. These were the loops were formed like a boundary condition on the equatorial plane. Okay, now so this actually created this configuration of striped jet. However, it is limited because we cannot follow the actual physics of what is happening within the accretion disk that may destroy the loop as they propagate inward. So a question may arise: can the loop actually survive the journey to the black hole? What is the efficiency of the launching process in this case, and what will be the effect of the dissipation from these loops on the efficiency of the launching process? This question could not be answered with force-free simulations, And basically, they can be answered by GRMHD simulations. And this is the study that I did together with Anya and together with Amir Levinson that we published a few months ago. And basically, what we did is that we took a disk, and we and the disk was sorry, it was published last year. My mistake. And the disk was threaded with poloidal loops. You see, with alternating polarity. Now, what you see here is that solid lines and dashed line represent polarity in opposite directions. And basically, when you start the simulation, the jet is built. Could I have? Is it possible to continue until 50 minutes?
Yes.
Excellent, good. So I want to show you what is happening to the launching of the jet when you accrete a single loop. Okay, so when you accrete a single loop, there are two accretion states that are basically discussed in the literature, which are known as MAD and sane state. MAD state is magnetically arrested disk. It is characterized by accretion of large-scale magnetic field on the black hole. Okay, and this, as I accrete the magnetic field, I will stop the simulation. As I accrete the magnetic field, basically I'm winding the poloidal field. Oh, sorry, I need to start it again. I'm winding the poloidal field, and I'm creating the jet. Okay, what you see in the image here above, this is the accretion rate. And at the top and the lower region, you see the magnetic flux on the black hole horizon. And you can see that during a MAD state, something weird is happening. Both the accretion rate and the flux on the black hole horizon that signifies the power of the jet, they fluctuate. I will explain these fluctuations soon. Okay, and this actually gives you an intermittent jet, the launching of an intermittent jet. As time progresses, the magnetic field inside the disk dissipates. I'm no longer able to accrete a large flux of magnetic field onto the black hole, and I'm entering a sane mode, which is known as stable and normal evolution. And with this mode, I'm only accreting small scale field. I have a low magnetic flux on the black hole, and I cannot launch a jet because I need the flux of large scale magnetic field in order to launch the jet. So within the MAD state, something very, very interesting is happening. So basically what's happening is that first I'm accreting all the magnetic flux onto the black hole and I'm creating the jet. But when I'm creating a jet, I'm also blending magnetic pressure within these regions which are dominated by the magnetic field. These are Poynting flux dominated regions. This is basically the base of the jet. Now these fields, when the magnetic pressure is large enough, they're basically trying to close onto each other, and they're creating a reconnection layer here on the equatorial plane, and plasmoids are formed. Now, this reconnection, basically what it is doing is detaching magnetic field from the black hole. Now, these fields is detached, so plasma cannot cross these fields, these magnetic fields, it's basically the accretion stops. As the accretion stops, more and more plasma is accumulated on this side of the magnetic field. The ramp pressure is increasing, and the plasma is pressing the magnetic fields inward, and I'm switching back to phase one. So this is basically the quasi-periodic behavior in the MAD state that we saw. This was done on a single loop. When we accrete several loops, we can also see that. So in this simulation, what I'm doing is I'm accreting. I'm taking two loops, one on left-hand polarity and the other one on the opposite polarity. And in the first stage that I saw you, I was accreting the first loop. And during this accretion, I launched a jet. I had a MAD state, and an efficient jet was launched. But here you can see on the right top corner, the second loop is coming in and starting to press the magnetic field of the first loop as it's pushing into the black hole. Now look what happens when I will restart the simulation. This loop will go in. It will compress this this is the loop of the first field that is compressed by this magnetic field, and it will induce reconnection within this first loop that will basically destroy and eliminate the magnetic field there, and I will have a flux switch on the black hole. Let me show it to you again. This is the mad state of the first loop. Here the second loop is coming, and you see the flux of the magnetic on the black hole switch direction. So I launched a striped jet. Now the jet is launched with an oppositely oriented field that is winded. Okay, so a striped jet is able to be launched during the also in MHD simulation. This is at least in the 2D simulation. In 3D simulation, we could reconstruct this behavior. This is the accretion of the first loop, and this is the mad state that is happening. This is the detach of the field lines from the black hole. However, this detachment is not complete. Basically, you can see that there are layers where we have the reconnection layer where the magnetic fields are unpresent, but they still have accretion on various directions because I'm breaking the spherical symmetry here. These are 3D simulations, not 2D simulation. Okay, but the basic evolution continues. Okay, so now I want to focus a little bit about what is happening in these current sheets, because this is the most important thing that I want to stress. So within the current sheet, as I show you, plasmoids are formed, and these plasmoids carry substantial amount of energy. Now the plasmoids are formed in two regions. In one region, they are formed on the equatorial plane during the mad state, and during the times where the flux is switching, the direction of flux is switching on the black hole, I'm actually producing plasmoid on the jet periphery, and you can see it here in the movie that I'm showing you. This movie is showing the here you can see the density. Here you can see the plasma beta, and here you can see the entropy. And you can see the formation of this plasmoid on the jet periphery. These plasmoids are very hot. They are propagating, some of them propagating inwards and some of them propagating outwards on the jet periphery, and they will radiate energy. Okay, they propagate at about 0.3 C. They may evolve if we continue to simulate them, and this is something that we plan to do in the future work. They may evolve into radio blobs that are sometimes that are you can see where they're moving out from lasers. Another interesting thing is that they're going to be very efficient emitter of X-rays, and they can illuminate the disk and be the source to excess of X-ray emission that is sometimes seen in accreting system that we cannot explain. The last thing I want to show you is that this may also explain the black hole shadow observation that was seen by the LHT collaboration. So these shadow observation actually were speculated to be created by these types of plasmoid on the equatorial plane. However, there are some discrepancies between what is observed and what is predicted by the simulations. Most importantly is the variation timescale. The variation timescales of these plasmoids are that were seen or on the order of days. However, in our simulation, we predict variation timescales of the order of months, which in order of magnitude larger. So the jury is still out whether these plasmoid can explain these features that were seen in the black hole shadow observation. However, I do not have a lot of time to further discuss it. So pros and cons. The launching of striped jet can have efficient dissipation at large distances, which can account for gamma ray bursts. It can also explain small-scale dissipation that can produce some observation features in AGNs. However, the cons are that the loop size is limited, and the formation of, most importantly, the formation of the loops is limited to about 100 RG. If loops are formed outside of this region, they will dissipate its magnetic field. The magnetic field will be destroyed before the structure of the loops will be destroyed before it will reach the black hole. So a main question that is happening, can these loops be continuously formed in situ within the disk? And for that, we need high resolution disk simulation to track the dynamo process that may create these loops. So this is another question that is happening. So to summarize, I show you several channels of activation and dissipation in Poynting flux dominated jets. I showed you the Kink instability, which is produced in collimated jets. It is efficient. It can efficiently dissipate magnetic energy at intermediate distances. It can dissipate about half of the magnetic energy, possibly more at longer distances. And they can signify massive HST1 like knots and in some laser flares. I also showed you how the striped jets can form. They can give you they can both give you intermittent jet activity, which is important for gamma ray burst. It can give you global reconnection at dark distances, and the formation of plasmoids and current sheets close to the black hole can account for all kinds of observational properties that we see, and to the creation of sub-parsec radio blobs. However, we still need to understand whether this mechanism can form self-consistently from the from dynamo process within the disk. So I will end here, and thank you very much for listening.
Okay, thank you very much, Omer, for this excellent talk. Yes, so clap our hands. And we will start with the questions. So Rodrigo, I saw your hand raised. You can start.
Thank you, Omer. Fantastic work. You presented a lot to unpack here.
Yes, it was a little bit.
A lot to wrap our heads around. Lots of interesting results. So, Omer, I would like to start with first a suggestion to try to connect your fascinating results with observations, which is, and this is something that should be, I think it should be easy to do, well, because it seems that I'm referring to the last part of your presentation where you show the current sheets in the jet sheet. You should be able to compute the luminosity being produced in these current sheets in the jet sheet, and probably if you have a suite of simulations, you probably can do some kind of scaling, see if that luminosity scales with the black hole mass or something like that. And
that's true. So
I'm suggesting, because this would be interesting because you mentioned the lamp. You put lamp, but I think you're referring to a lamp, right?
Yes. Oh, sorry, that was a typo.
But if you give maybe if you give numbers for this luminosity from the jet, from the current sheets, then the observers of stellar mass black holes can compare with your model, right?
So this is definitely the goal of our next research. The problem was in our previous research that we had enough resolution to let's say to catch this plasmoid only in 2D simulations, which are they are less reliable. In the 3D simulation, we just did not have enough resolution. We could speculate from analysis, from process analysis, the formation of these plasmoids and current sheets, but we could not really catch them. Now we are planning a much higher resolution study with AMR-based codes, together with Bart and with other people from the CCA and from Harvard. And what we want to do is we want to do exactly that. We want to try to catch these current sheets and to calculate the actual emission properties from them. So this is kind of a stay tuned. Maybe we'll have some results in, I don't know.
Can I ask a second
year or two? Yes.
Sure. Yeah.
So my second and last question is, so as you know, the origin of flares, we see a lot of flares in blazars, especially with the Fermi telescope, which is a blazar machine. And we really, for decades, we see these papers about observing blazar flares patterns. Several people have studied systematic trends in blazar flares. And my question to you is, of course, I understand that you see periodicities from your Kink instability simulations, correct? You see periodicities, right? Like sort of TPOs.
Well, the periodicity that I discussed is actually coming from the launching process, not so much from the kink.
Do you think the kink could possibly be associated with perhaps flares in the jet?
So the way that I see it, if you have an intermittent jet, okay, and you have like a plasma blob that is passing through the collimation nozzle, then this will definitely give you a flare. If you have a stationary through the blob, and sometimes you have periods of higher efficiency, and this region can dissipate a little bit larger amount of energy, and then you see there's this. Sometimes you see rebrightening of this AGST1. If you're talking about flares that give you a very large rebrightening, one possibility is that maybe if you have an intermittent jet, and then you see this blob that is passing through the recollimation nozzle, and then you can see a flare.
Okay, thank you.
Okay, thank you. And let's move on with Betch. You can ask your question, please.
Oh, hi, Omer. Here is Elizabeth Gouveia Dalpino speaking. How are you?
Hi, Elizabeth. I'm good.
Yeah.
How are you?
Fine. Yeah, I think the last time we met in person was in Princeton a few years ago.
I think so, yes.
Yeah.
Yes, that was a long time ago.
Yeah. And you know that we have been going through all these processes, studying all these processes on reconnection and kink unstable jets, as you know. And so I have several questions, and if I may. And the first one regards this study that you are doing now on the kink with the rotating jets. And the results that you showed, because you probably know that with the Singh and Mizuno in 2015, we studied the kink in rotating jets, and the results are the results are very similar actually to the non-rotating ones, as you pointed out, very similar to the effects that you showed. But I was wondering what was the range of rotation velocities that you applied in your study.
So this study is still in an initial phase. Okay, it's an ongoing process. These are still ongoing simulations.
Okay.
And the rotation.
You did not publish this yet, right?
No, it's not published. It's not published. Okay. We are still conducting it. Okay. The rotation that we are using at the moment, I think, are something like omega is a few 10, like omega is like 0.3 or something like that, 0.4. It's not rotating very fast, but it's rotating in a non-negligible way.
Right. Which is reasonable. Yeah, it's anyway. It's worth sweeping this parametric space.
Yes, definitely, and we're doing it, and we're definitely doing it.
Okay, good. Now, regarding reconnection acceleration, right, both in jets and in the surroundings of the accretion flow, I have a comment on this because when we talk about plasmoids, actually this is two-dimensional reconnection, or in other words, it's just the two-dimensional cut of three-dimensional flux.
Yes, they're actually elongated tubes.
And the flux stuff actually, and reconnection is actually reconnection acceleration is actually a three-dimensional process, right? And this thing, and so plasmoids are actually, the ultimate stage of reconnection sheets, because when you have a turbulent flow, you have these three-dimensional flux stubs reconnecting everywhere.
Yes.
Then you have you have fast
these tubes. You have something that look like a tube that when you look it from the side, it looks like a plasmoid.
Exactly. And then, but the key point here is that you do not need actually too much high resolution in order to see particle acceleration in three-dimensional reconnection driven by turbulence. This because turbulence survives on all scales, from the injection scale of the turbulence at the largest scales, let's say for the jet, of the order of the jet radius, down to the dissipative scales, right? Of that are probed by the resolution, the numerical resolution of your simulation. So the key
You're
point.
talking about the peak now, or about the MHD?
I'm talking about MAGD, right?
MHD, okay.
Okay. So,
yes.
So in this sense, it's very nice because we can see particles being accelerated from the small energies where they are interacting with the small scale structures of the turbulence up to the very large scales when the alarm radius actually gets bigger and bigger because they are accelerated. And then they are still being accelerated by this stochastic Fermi-like dimensional reconnection process up to the injection scales. And that's why in the simulations that you probably have seen, that we injected test particles, because Chandra Singh is also a co-author in this, and we injected particles in the three-dimensional Kink unstable jet, relativistic jet. These particles are accelerated from the very small scales up to the larger scales, up to ultra high energies, right? Because they still interact resonantly with the current sheets at the larger scales, because those larger scale current sheets are also present in the larger scale up to the injection scale of the turbulence. That is of the order of the jet radius. So in this sense, you really do not, if we understand three-dimensional reconnection acceleration as driven by fast reconnection by the background turbulent flow, we are happy because we can see, we can think, we can seek out this process in MAGD simulations from the injection scale down to the resistive scale. And of course, but then, okay, if we compare with peak, because peak can only probe a few hundreds of the skin depth, then, okay, you can accelerate only up to these scales. So you see only the smallest energized energies of the accelerated particles, right? So in this sense, both cases are very complementary, and I believe that a key point that you explored in Gavilar et al. Was the fact that you really try to explore this process in highly magnetized jets, right? Yes. And this is a very important fact, because, you know, sigma equal 10, 100 is almost, 10 is fine, but 100 in MAGD simulations is very hard.
Almost impossible.
Yes, almost impossible, right? So in this fact that you explore the magnetization and realize that the higher the magnetization, the steeper is the spectrum, is an important finding, right? But essentially, in our simulations, when we had this sigma equal 1, this magnetization 1, really you find that the particles and the spectrum is very flattened, because you get very high energy particles, because we understand what is going on with this three-dimensional reconnection driven by turbulence, which in turn is driven by the Kink instability, right, in this case. So I think these studies, there is a lot of things, as you said, that we still have to understand, but I cannot agree with this point that you really need a very, very, very high resolution in order to see the small scales, because, okay, the small scales, you are going to probe acceleration only up to those scales, or a few hundred times the rest mass of the particles. But to probe, you know, particles to the largest scales, of course, we have to, the Larmor radius of these particles, we increase up, and then will be accelerated as long as they encounter these fluctuations that start to be produced at the injection scale of the turbulence. And this also applies to the GRMAGD simulations of accretion flows. And we also identified in our GRMADD simulations, that MRI drives this turbulence, and then we have all these current sheets in 3 dimensions, or in other words, reconnection sites in all parts of the turbulent system with the fast reconnection, right? So again, there is this argument, of course, one has to understand or to accept the fact that turbulence drives fast reconnection in a system, no matter what is the physical mechanism that drives this turbulence in the system, right? In the case of accretion flows, essentially the MRI can do that. In the jet, the kink instability is a very good mechanism to do that. But anyways, I think that the physical principles are the same. And I also see that this study on polarization that you are doing is rather important as well, both in the accretion flows, and we are also searching this process, trying to figure out, understand this process.
It's more complicated than it sounds, that's the problem. Everything regarding polarization is more complicated than it sounds.
Exactly. Yeah, so if I may, I would like to make a last question, perhaps. If
yes, of course. Yes, go ahead.
It's the striped jet model that you showed, because the one that I'm familiar with is the one by Zhang and Giannius, one that they proposed to study this, this effect of a dissipation along the jet. And in this point, the dissipation, because no one really knows, for instance, where is the blazar zone or where is the dissipation zone in this relativistic jet, right? Where it leaves the magnetically dominated and start to be kinetically dominated, right? And in this regard, actually, coincidentally, last month I gave 1 month ago I gave a colloquium in Princeton to the astronomy department and the Institute of the Advanced Studies, exactly on this, particle acceleration by reconnection in relativistic jets subject to Kink instability, and the origin of very high energy emission and also neutrinos, right? And I was asked about this point, the dissipation, and how to associate this dissipation region with the luminosity of the jet, and how this luminosity is related to the luminosity of the accretion, or not the accretion of the Eddington luminosity, right? Because right now, I don't know if you have heard about this crisis of emission crisis in blazar jets towards the very high energy, because they say, okay, if you have leptohadronic processes, if you have hadronic process, maybe that allow for the production of neutrinos, both simultaneously, neutrinos and gamma rays, then you may have a crisis, because they find that for several classes of blazars, the luminosity of the jet power has to be 1,000 times the Eddington luminosity, and this is not allowed by the launching models like blend 4 is Najek, or even blend 4 in Payne, if it comes from the jet itself. And then they asked me, oh, so you were showing a process, and then I showed to them that with reconnection, producing, accelerating the protons, and these protons producing the gamma rays and the neutrinos, we only need this luminosity of the jet power to be of the order of 10, at most several dozens of the Eddington luminosity. So we are not in this crisis, right? So reconnection can solve this problem too. So I wonder, what would be your answer in this case about this crisis, this blazar emission crisis, if you are familiar?
The main problem with the striped jet model is that it is not completely clear, even when the striped jet will collide with each other at some point. It is not entirely clear how efficient this the reconnection is going to be, because in the end of the day, we still have two layers that are moving at the relativistic velocity, right? The Lorentz factor may be different, but within the common frame, the rest mass frame, the center of mass frame, sorry, the relative velocities are not very large. So the question is, how quick is going to be this collision? The quicker the collision will be, the more efficient your emission is going to be.
Right, right. Mm-hmm.
So I don't have an answer to that, because I still don't know how efficient this collision is going to be, and this is something we definitely want to study. At the moment, we only focused on the launching process to see how efficient is the jet launching from this type of accretion of oppositely polarity loops. What we find is that we can get to an efficiency of to similar efficiencies that you get from the launching of Poynting flux dominated jet from a single loop, which is something like, I don't know, 30-40% of the accretion rate.
Right.
Okay.
Mm-hmm.
So these are very efficient jets, but how efficiently they will emit the energy, I still don't know.
Right, right. Mm-hmm. Yeah, actually, we've been studying this as well, and I can send you the
I will be happy to look at it.
Results, yeah, using as a toy model the striped jet model. So it's interesting because it works. I mean, of course, constrained by a parametric space, but it might be possible.
Okay.
It might be. Okay, so thanks a lot. Sorry, Maria Victoria, for
no problem. Thank you for the discussion.
Oh yeah, I think this is more alive. This discussion,
workshop discussion.
Yeah, it's more interesting. Makes the colloquium more interesting.
Yes, because we don't have a coffee break, so this is the place to do this. Actually, this is the moment.
Actually, yeah, that's true. Mm-hmm. Okay, so thanks a lot, and say hello to the common colleagues, to the friends there.
I will definitely. I will. Yeah. Definitely.
Okay. Nice to talk to you.
Likewise.
Okay, so I have a question regarding also the comparison with the luminosities of the jets with but it's not so ambitious like the other questions, because I am wondering if you can just simply relate the dissipation rate that you got from the Kink, for example, with the total luminosity in X-ray to radio in HST1 not, for example, of M87, and if it's
yes, we can definitely do that. Yeah. It's actually a good idea. We didn't do it,
okay.
But I think it's a good idea to do it, because it's also possible, because there are estimates for the jet power, so we know how much power there should be in the Kink jet, and yeah, it can definitely be done. It's actually can be an
maybe you can.
Number.
I'm not sure how, but maybe this can help to get some idea of how efficient the radiation mechanism is, and if you are lacking some power somewhere, or maybe you have too much power.
That's actually an excellent idea. I will definitely try to look into it. I didn't think in the directions. Thank you.
You're welcome. So I think if there is no more questions, okay, so we or I am going to thank you in name of all of us. Many thanks for your wonderful talk. Many thanks for the discussion. And well, I don't know if you want to say something.
Well, thank you for having me.
Okay.
It was really fun giving the talk and conversing finally with people outside of my department, after 2 years that all I do is this.
Yes.
Like talking with people. I'm talking to people that I know. It was a good thing to talk to other people that I know from abroad. So thank you very much for that, and I hope that maybe we'll be able to do that again in person.
Yes, we will be very happy to invite you in person once. So thank you. So
Okay.
we will finalize the transmission through the YouTube, so we can